Welcome everyone. In this video I will try to improve my previously introduced cooling box. So if you check my previous two videos, you could see that I was trying to build a cooling box, and that cooling box was using a TEC12710 Peltier cooler. So I was using just a single Peltier cooler, an 8 ampere unit. I was trying to run it around 4 to 5 amperes. I was using a CPU cooler to cool the hot side, and I attached a smaller heatsink to the cold side and also a fan, so that was circulating the air inside the box. And I tried to make sure that the entire volume of the box is cooled properly. But after some measurements, I concluded that the cooling was not sufficient. I tried to make some improvements, so that's why there are two videos for the first iteration. But seems like something is wrong. Either I just messed up the contacts between the hot side and the CPU cooler, so the real hot side temperature is warmer than the air temperature that I can measure in between the fins of the heatsink attached to the hot side, or this is what it is right now. So in this video I will make an improved cooling system with a much better performance, or hopefully much better performance, and you can see the tools for that on my desk. So let's start with one of the most important parts, which is the cooler of the hot side. So I will use this Arctic Cooling Freezer 7 Pro CPU cooler. I have removed the fan, but I will use another fan on this CPU cooler. So based on the manufacturer and other data sheets, the performance of this is somewhere around 130-150 watts, but the recommended power that you should introduce to the hot plate here is around 115 watts. So we will limit ourselves somewhere around, let's say, 120, and we will see what will happen. But there is one significant problem with this thing here, which is the hot plate size. So this contact area is only 3 by 3 centimeters, while we know that the Peltier cooler is 4 by 4 centimeter. So if I put the Peltier cooler hot side on this area, there will be an edge which is 5 millimeter wide exposed on all the four sides. And I don't know exactly, but I assume that that's not a good thing, because you have the semiconductors under this ceramic plate almost until the edge, which means that there can be a significant temperature difference between the very middle of this unit and the edge of the unit if you have the sides exposed. So I thought that it might be a stupid idea, but let's try this. So I made these plates from pure copper. So I had some longer bar or sheet, I don't know how it's called, which is exactly 4 centimeters wide. So it's the same width as the Peltier cooler. So I just had to cut it. So I just used some hacksaw and cut it. So what I will do is that I have the hot side of the Peltier cooler. I attached this, so we have still a homogeneous area here, and then the gradient, because of the exposed edge, will be between the copper plate and the CPU cooler, instead of directly connecting the Peltier cooler to the CPU cooler. And why I think this is better is because the copper plate has a relatively good, or not relatively, a very good heat or thermal conductivity. So I would say that the heat from the hot side of the Peltier cooler to this body would spread nicely, and this will act as a sort of a buffer zone. And when I attach the CPU cooler to the plate, then the Peltier cooler would feel a bit less inhomogeneity between the middle and the edge of the Peltier cooler. So that would imply, at least for me, that there is less stress on this regarding the, let's say, thermal stresses because of the uneven temperatures. So yes, this might be wrong because I introduce extra surfaces or thermal resistances, because now instead of having just thermal grease in between the two surfaces, I have actually two thermal grease surface. One is between the Peltier cooler and the copper plate, and then the other is the copper plate and the hot plate of the CPU cooler, plus we have the copper plate. But maybe it is still a better idea than just directly connecting like this. So we will see. So this is why I have the CPU cooler with this two copper plates, and now, as you could have guessed, I will use two CPU coolers, two Peltier coolers to realize this cooling. So we have roughly let's say 240 watts of cooling power available, and that cannot be translated into 240 watts cooling power on the Peltier coolers, of course, because they generate heat just because of the Joule heating. So based on the current and the voltage that you use to run the device, there will be some amount, U times I, rejected heat on the hot side, additionally to the pumped heat which comes from the cold side to the hot side. So the sum of these two amounts have to be dissipated with this, or with these units. So what we will able to do roughly with these units, which are the 12710 units, so I went up 1 unit more. As you remember, the previous was 8 ampere, this is 10 ampere unit. So I went up, and what I expect is roughly 35-45 watts of cooling power per unit. So in total, let's say we have something like 70 to 90 watts of cooling power for the total system, hopefully. But we will see that. So then we discuss the Peltier coolers as well. So the cold side will be this 15 times I think 6 times 4 heatsink. So I drilled 4 holes, and these will be used for the clamping mechanism. It's a very lucky coincidence that we have the nuts, which I can show you soon here. So these kind of nuts, I think this is M3, they fit perfectly in between the fins. So if you see, the parallel sides can be fitted in between. It's a very snug connection. So then I can use these aluminum plates, which I just cut again from a strip and drilled it to clamp down the coolers. So basically what I will have here is I have the two Peltier coolers. Now this is just a rough assembly, and then I have the two copper plates, and then each side, and they fit just perfectly next to each other, so the walls or the lamella will just barely touch each other. So I have the two coolers like this, and then I just slide in these plates, and we already have the screws, or the nuts, sorry. So the nuts are there, and I will use these special screws because I cannot really use a screwdriver once I'm putting everything here. So when this comes here, as you can see, then this screw, I will put the name somewhere here. I don't remember how it's called. This will be just here. And then I can manually, or just by using a plier, I can nicely tighten the screw. So this will be the assembly, and we also have this nice foam. As you can see, the shape, this is specifically for Peltier coolers. So I will glue this thing on this surface like this. I have to cut it a little bit, but that's not a problem. Maybe I will put it like this. And this will make sure that we decrease the heat transfer between the back of this plate and the environment. So the cold side will be exposed towards the inside of the cooling box. So once again, let's say this side is the inside of the cooling box, and then the next layer will be the Peltier cooler, of course on its edge, but I just want to show you in a nice like diagram. And then the plate comes on the top of the hot side, and then we have the CPU cooler, and we just use this plate to clamp it down. So this will be like the order of layers. And of course here, here and here we have thermal grease. That's obvious. So before I proceed to assemble this thing, I want to quickly show you something on the computer. So what I want to show you on the computer is just some rough calculation or rough estimation. I will also show you how to size your Peltier cooler based on an available cooling power. And by that we will be able to select the amount of heat that we can pump from the one side to the other, or the DT, so the temperature difference between the cold side and the hot side, and so on and so on. But yeah, let's just go to the computer, and I will show you some charts and some very easy calculations. So as I said, I will go through the performance chart of the TEC12710 unit. And what you can see here is my own plots. So I sort of digitalized the data sheets, and then I plotted these data myself. So for me, it's more easy to go through the data because I see all the functions and everything. But we would like to see how we can power this unit, right? So let's write down what we have. So we know that the available cooling power is roughly 120 watts per CPU cooler. So I just write down that the CPU cooler can provide roughly 120 watts. So we are looking for something where we can get the joule heat plus the pumped heat at around 120 watts. So that means that this 120 watts should be divided into two terms, which is the P, and this is the I times U, and this Q is basically just the heat which goes from the hot side to the cold side. So basically the Q comes to the cold side, and then it appears on the hot side. And why is it like this is that one thing is that we move the Q, so that's the pumped heat that appears on the hot side, but we also run the device, and because this is basically just a resistance or resistor, we have to take care about we have to consider the joule heating as well, and that is just the product of the current and the voltage. So this basically gives us some sort of suggestion that at which current we should run our unit. So we also know that the desired temperature, so let me write it down, so the desired T should be at least under 4 degrees Celsius. And then we also know that we have an available power supply which is roughly at 12 volts. It's a bit higher, and we have 30 amps available. And of course this is still an overkill, because in the worst case we will run these units at 10 amperes. So if we run them at the highest current available or highest current possible, then we just use 2/3 of this available current. So we don't care about this, but we can start from this 4 degrees Celsius. So from the 4 degrees Celsius we know now, or we can estimate what should be the difference between the hot side and the cold side. And of course, the more we approach this 120 watts power, the higher will be the hot side. So what I would like to do, and this is just sort of a rule of thumb, that we should aim roughly for 30 to 50 degrees Celsius DT. So that means that the hot side, which is TH right here, is roughly around, let's say, 34 degrees Celsius to 54 degrees Celsius. And this is like a highly idealized thing, but it makes us easier to do the calculations. We have losses, we have all other stuff, but this is just a rough estimation. So based on these things, we can sort of restrict the region. So we are somewhere at 30, so this is 30 dt, and then this highlights the available current and QC pairs, and then we should also draw a line here at 50 degrees. So now we are narrowed down our region of interest, let's say, in between these two lines. So then now we have to look at this 120 watts, and just if you look at the charts, you get the rough like impression of the current that you can use. So I will not draw on this chart and not calculate, just tell you that, for example, if we go for 10 amps here, so that's the cyan color, and we want to have, let's say, we can cool the hot side very well, we are at dt equals 30, so now we can pump nearly 70 watts, so we have 50 watts left here. But here you see that we have almost 150, so 10 times 15 almost. So now we know that our device runs at roughly 12 volts. So first of all, let's start from that point. So first we look for the 12 volt, and each of these tick is half volt. So this is 11, 11.5 and 12. So we draw a horizontal line here. And now we see where it crosses, and you see that it crosses the 8 amps. So if the DT is around 30, just to be easy, or 32, then we are at 12 volts. And that also means that we are here, so nearly 60 watts of cooling power, roughly 54, let's say. But if you consider that, so now 12 volts and 8 amps, that's 96 watts, plus, let's say, 60, so that's 156, so that's too much. And if you allow further DT increase, you go down in current, and that's not necessarily good for us, because if you go down with current and increase the DT, you end up somewhere here, and that is a very low power. So let's go somewhere to the middle, and now let's go the other way around. So let's say we want to go for roughly 6 amps, and I think that's a healthy estimate, because based on this setup, I think we will be somewhere between 6 and 7 amps per unit. So we are at 6 amps, so we only move along this green line, and then let's go just in the middle somewhere here. So that should be 10 volts roughly, and dt equals 40. So let me write down. So U equals 10 volts and dt equals 40 degrees Celsius. And then if we go up along this line, we end up somewhere here. So halfway we are at 30 watts, and then halfway again, this is, let's say 35 watts. So here the QC is 35 watts. So what we have here is that we run at 6 amps. So let me write that down as well. So 6 amps, 10 volts roughly, and that is 60 watts for now, and we have 35 watts. So this is together is 95 watts. So we still have a reserve of let's say 25 watts. And let's leave it like this, because I'm sure that the numbers here will be higher. So we will be using this in the real experiment. But now this is very good. So what we learned from this is that if we run our device at around 10 volts, or we have around 6 amps per unit, then we can achieve 35 watts of cooling power. So then the total cooling power will be 2 times 35 watts, very ugly 5, sorry. So that is 70 watts of cooling power, and this is now getting somewhat significant. So 70 watts of cooling power, and then 120 watts of rejected heat in total due to the Joule heating. So the total heat, let's say, is made of 2 products, so P plus Q, right? And then we have 2 units, so let us already consider this. So the P term is 2 times 60, plus the Q term is 2 times 35. So then we get this 120 watts, and this is the P, plus 70 watts, and this is the Q. So in total, as I said, this will be 190 watts of heat generated. So it's a small heater, very small, but in exchange for that we get quite a nice number. And then actually we can calculate the COP from this. So the COP is basically just the gained cooling power divided by the invested heat, which is in this case roughly 0.58. It's not too bad. It is okay for this kind of system, because we are not looking for efficiency, but we are looking for performance right now. So you can see that if you know the limits of your cooling system, and if you know what is your desired temperature, at least some range, and what is the available power supply, then you can roughly estimate the cooling power that you can achieve using the performance charts. So now, after this summary, let's go to the experiment and let's see how the cooling box behaves, and let's see if we can get the same numbers as we can see here. So I assembled a new system with the 2 TEC12710 Peltier coolers with 2 individual coolings, and then you can see the different parts here. So the temperature logging system is the usual system. So it's a 4-channel digital thermometer. Here we monitor the room temperature, and there are 3 different thermometers inside the chamber, as you can see on the picture. So I took a picture before closing the lid. And then we will monitor the temperature for the hot side with this thermometer. You can already switch it on, and this is basically the initial temperature, so 25.3, let's say. Then the power supply is here. So there is a thicker cable here that will provide the power for the 2 Peltier coolers, and then this thin cable is for the fan inside the box, and the fan is a 4 centimeter 12 volt fan. It will run on the maximum RPM, so the circulation of the air will be strong, and you can also see it on the picture, which I put here on the video. We have another power supply here that is for the 2 8 centimeter fans, which are pushing the air through the CPU cooler. The air will go upwards, so we will have the natural convection of the warm air, and basically that's all. So what I should do now is I should turn on the things, So now I turned on the power supply and only 2 units are running now. One is the cooling for the Peltier cooler. So I wanted to make them independent from the power supply because I already want to have some airflow before I turn on the power. So 2 fans are running, as you can hear it from the background noise right now. And the logger is also running, that is powered by this mobile phone charger. And again, I will log the temperature on an SD card, so after this experiment we will be able to check the temperatures and how they evolve. So the only thing which is left is I have to plug in the main power supply, which powers the Peltier coolers and the fan inside the box. So as I attach this, then roughly 12.1 volt will be given to the 2 Peltier coolers, and that should provide roughly 6 amperes per unit. I connected the Peltier coolers parallel, so they get the same current. So let me connect this. Now you can hear that this is running as well. And let's measure the current. So I turned on the logging, and this is the current, 13.7. So you have to divide it by 2 to roughly 6.8 amps per unit. So now what we should see is that the temperature on the hot side is increasing, as we would expect. And I can tell you that the cold side is already at 15 degrees now. So time starts now, and I will run this for half an hour, and then I come back and tell you the values that we can see. So the experiment has been running for a little bit more than half an hour, so let's check the temperatures. So first of all, the hot side here is very cold, so 32.5 degrees Celsius, so roughly 7 degrees above room temperature. Let's see what is the current right now. So I just measure if it changed or not. So as the temperatures equalized, then we reached 13 amps for the total power, or total current, sorry. So that means that each unit is running at 6.5 amps. Then if we check the temperatures inside the chamber and here, so first let's check, the room temperature is 24.5 according to that meter on the top of the lid. The cold side heatsink temperature is minus 4.3 degrees Celsius. The thermometer in the middle of the chamber is 9.5 degrees Celsius, and the other thermometer in the corner is 10.3 degrees, so they are quite close to each other. So now we have to wait and see where this goes, but based on the fact that the cold side heatsink is minus 4.5 degrees, we can expect much more colder temperatures inside the chamber. We just need some time to properly distribute the cold air. So let's wait another half an hour and check how this experiment goes. So another half an hour passed, so let's check the temperatures. So first of all, this is the hot side, still unchanged, so 7 degrees above the room temperature, which is very nice. So seems like this cooler is good, and also it seems that the copper plate that I introduced in between the CPU cooler and the hot side of the Peltier cooler can transfer the heat very efficiently. Then the cold heat sink is minus 5.5 degrees Celsius, so that's very nice. And the internal temperature inside the chamber is between 8.3 and 9 degrees in the 2 different thermometers. So this is very nice. And now we see that the temperature of the chamber, or the change of the temperature in the chamber, started to slow down. But I'm a bit concerned about some leakage or something like that, because the cold side heatsink is 13 degrees below the temperature of the chamber. So that suggests me that there is still heat to be distributed in the system. More precisely, there is more heat to be removed through the cold side. So we could increase the temperature of the cold side by at least 9 degrees to go back to 4 degrees, and we should be able to cool down the air inside the chamber more. So let's see where we end up in another half an hour, and if we don't get any significant difference, then I will review the box and see some possible improvements. So now the experiment is running for 1.5 hours. So this will be the last check-in with this kind of setup. So the hot side temperature is still 32.6, so 7 degrees above the room temperature roughly, and that's very good news. And if I check the other temperatures, -6 degrees on the cold side heatsink, and inside the chamber or box I have 8 and 8.8 degrees Celsius. So this means that something is going in the very wrong direction inside the box. So I think that the circulation might have been messed up or something like that, and that issue needs to be addressed. So what I will do now, still within this video, first of all I will clad the inside of the box with the aluminium foil as it was suggested by one of the viewers, and we will see if that works. But I agree that that should work, and it should help at least keep out the radiated heat. But actually then the aluminium foil should be on the outside, but that doesn't matter. And I will look for leakage, so I will try to make it even more airtight, and we will see. So I will come back, and then I will show you the improvements for the box, and we will run the same experiment again. So before starting the new experiment with the new setup, I want to show it to you. So now you are looking into the chamber, and you can see the connections and the 3 new fans. So I installed 3 tiny fans, as you can see. So the air will be circulated through the entire surface of the heatsink, more or less, as you can see. So we have 3 12-volt fans, and everything is covered. Even the lid is covered with aluminium foil, double layer on the walls and the bottom. So this should be nice. And now what I will do, I put back the camera to the tripod and just continue the discussion. So fix the tripod and fixed everything. So we have 3 thermometers inside the box. One is attached to the cold side heatsink, one is in the middle, and the third one is in the other corner of the box. And then one is also placed here. That is the room temperature, and this is the temperature of the heat sinks right now. So nothing is running yet. So I just turn on the extension cord here, and now you can hear the fans for the cooling of the hot side, and this also started the temperature logger. So we will log the temperature again with this new setup, and we will see what happens. So before powering on the Peltier coolers, I just turn on the logging. So now we are saving the data on the SD card, and now I just power up the Peltier coolers, and this will be noisy because of this power supply. So now this is running, and 13.7 amps in the beginning, of course. So now we have to wait like half an hour, and then we can draw our first conclusions about this improved system. So 2 improvements now as compared to the previous box. I cladded the inside of the box with aluminium foil, and I added 3 small fans to cover most of the heatsink with airflow basically. So if you remember, a few minutes ago I showed you a picture where there was ice on the 2 sides of the heatsink, which was not covered with the fan. So there was no airflow and ice could form there because it was really cold there, colder than the place where we had the fan. And if you look at this temperature, this will be basically our equilibrium temperature, if I can say so. So this will be the hot side temperature measured on the CPU cooler. So let's wait half an hour and let's come back and see what happens. So let's make a half an hour report. So the experiment is running for half an hour, and this is the hot side temperature measured on the CPU cooler, 32.8 degrees Celsius. The room temperature is 24.7. The cold side heatsink is 4 degrees, and then inside in the middle we have 8.5 degrees, and in the corner we have 8.8 degrees, so they are pretty much at the same temperature. And we can see that now the temperature is changing a little bit differently than in the other case where the inside was not covered with aluminium. So this was a good thing. So now I will wait another half an hour and see what will happen. But before going there, I will just measure the current. So if you remember, it was 13.7 when I started, and now 13.6, because the temperature of the Peltier device changed, therefore the resistance of it changed, and this caused this kind of difference in the current. So now roughly 6.5 amperes is applied per unit at 12.1 watts. So this is now our condition. Meanwhile, the temperature on the cold side heatsink dropped down to 3.7. So we wait another half an hour and see what is the result. So the experiment is running for 1 hour now, and we can check the temperatures. So let's start with the hot side temperature, which is 32.7. So it's pretty much the same as previously, just a few tenth of degrees change. And the temperature here, the room temperature 24.7, the cold side heatsink temperature is 2.5 degrees, so almost at freezing point. And then in the middle of the box we have 6.5 degrees, and in the corner of the box we have 7 degrees. So you can see that we almost reached our goal temperature in 1 hour, which is quite nice. My goal temperature would be 4 degrees, so I continue this experiment for another half an hour and I see if I can reach that low temperature. So let's check back in half an hour. So we are a tiny bit over 1.5 hours, and we should check what are our numbers. So let's check the hot side temperature, 32.5 degrees, so it hasn't really changed. And then the cold side heatsink is 2 degrees Celsius, and in the chamber we have 5.8 in the middle and 6.8 in the corner, so 1 degrees difference, but really close to 6 and 7 degrees. So that's very nice. But seems like that now we are in the flat part of the curve. So what I would suggest for the last half an hour is, while monitoring the current, which is right now 13 amps, so 6.5 per unit, I increase the current to, let's say, 7 amps per unit, which would mean that on my current meter I should read 14 amps. So what I will do now, I increase the voltage on the power supply a little bit, and then that should increase the current. So 14.16 amps. I slightly went over the current because this will change a little bit when the temperature is changing throughout the units, so there can be some decrease in the current And now if I check the hot side temperature, then it's slightly increased. So we wait another half an hour and we see what will happen. So this is the last part of the checking of the temperatures. So let's check what happened after I increased the current by half amperes. So you see that we increased the temperature roughly by 1 degree on the hot side cooler, on the CPU coolers. Room temperature is still 24.5 according to this thermometer here. The cold side heatsink inside the box is increased to 3 degrees now. 2.73 is jumping in between those two values. And the overall temperature inside is now 7 degrees. So in the middle we have 6 degrees, 6.3, but on the other corner in the box we have 6.8 degrees Celsius. So roughly 1 degree difference, let's say. And we are at roughly 7 degrees inside the box. So now I just shut down everything here and I plot the numbers which are saved on the micro SD card, and then we finish the video. So let's go to the computer. So now we are looking at the two curves from the two different measurements, and let's take a look at them and compare them. So you can see that the room temperature is pretty much the same. The solid line represents the data for the first test and the dashed line represents the data for the second test. And you can also see that the second test was longer by half an hour. That's because of the last test where I was curious about the effect of the increased current. So then if we go towards the other curves, let's first look at the two thermometers which were placed in the box in different places. So the green solid curve was in the corner and the red solid curve was in the middle of the box. You can see that the temperature difference is not too big in between them, so it's like 1 degree difference, and therefore they follow each other very nicely. And the same applies for the second experiment. In the case of the second experiment, the whole set of curves regarding these two thermometers is shifted down by 2 degrees, but the temperature difference between the curves still remained 1 degree. So I guess that has just something to do with the convection or the heat transfer inside the box. And then there is a huge difference between the cold side heatsink. That can be explained by two reasons. One reason is the different configuration of the fans. So in the case when the cold side was able to go down to -5 degrees, that was because we just used one fan in the middle of the cooler or heatsink, but we were measuring the temperature on the side of the heatsink. If you remember the picture, then you could see that the cold side heatsink was quite icy on the sides, and I put the thermometer on the left side and it was measuring the temperature there, far away from the area which was more affected by the airflow. So that can be one of the reasons that we have some different temperatures. And also due to the added airflow to the sides. So when I used 3 fans, then I was able to remove more heat, and therefore, of course, that was one of the reasons why the temperature went up and the overall temperature in the box went down. But still, there is a question mark for me that why the difference is so big in between those, and why the temperature difference is so small between these. So I mean that here we got like 8 degrees difference in between this temperature and this temperature, but then the temperature difference between the box internal temperature is not different by 8 but only by 2 degrees difference. So I don't know where does that heat go, or where did that heat go. So that still needs some small explanation. And one thing what I want to notice here is seems like that the increase of the current was a stupid idea. So instead of this, I should have decreased the current. So in the next video, I will try to do that, and I will just make a quick, maybe 10-minute video about this to have the exact same equipment. I will not move anything. I just put a new power supply there, and I will just run it at, let's say, 12 amps or 11 amps. So one unit will experience 6 or 5.5 amps, and we will see what will be the temperature after, let's say, 1 hour or 1.5 an hour. And based on that, I think we can finally close this investigation, and we can focus on something else. So I hope that this long video was somewhat useful to you. I hope you enjoyed it, and I hope you could get some ideas or some tricks and tips or something like that. If you liked it, please subscribe to my channel. That will help me a lot. Please leave a comment if you are interested in this project, or if you want to ask some questions related to Peltier cooling or something else. You can also visit my website, where I usually upload some extra things, for example some pictures or this chart or something else. My website is curiousscientist.tech, and I think I finished this video right now, so see you in the next video.